We contracted a company that used ferro laser equipment, kind of a cool device. They set it up on site to get the geometry of everything that's going on. So the ferro works, they call it a laser tracker. It measures 2 angles and a distance. And the tracker sends a laser beam to the, we'll call it the target. And what's cool is when they're moving that target around, and let's say this is the target and this is the laser, as I'm moving, this head is rotating. I touch this surface, I touch this surface. So they were measuring. This thing was tracking every measurement and movement. The tracker would rotate 360 degrees. So if I carried that sphere around, the tracker would just follow it, as long as you didn't get too aggressive and get out of the laser range. Cool device, but what was really cool is the accuracy. I don't remember the details now, but at quite a distance, you had up to 2,000ths. At closer distances, you had up within 1,000ths of accuracy, which is really amazing. So nevertheless, we had laser measurement done. We still measured and cross-measured. I needed a reference information that when they gave me the information from the laser info, I had some way of going back and confirming that, yep, the coupling is that, yep, the shaft is, looks to be about those numbers, blah, blah, blah. So we were on site as well measuring. And here, this was the tabulated result. And what this view is just showing the details of the shaft. Because what I realized is we were going to have to duplicate that shaft for our machine. So went through all of those details, and on top of that, we had to look at the base of the pit. We had to look at the location of the bed plates, where we span to be able to support the motor like the original. So all these details were taken. This took quite a bit of effort, and also I'm quickly going through this, but I had them do this 3 times. And I did that on purpose because they did the first one, and we had a few questions from our measurements. I had them go back and do another one, and they messed up. Their calibration was wrong, and they did the whole scan, shut the customer down, did the whole scan, and the data was wrong. And I spotted that right away, so I said, look, guys, you have to come back. I need another redundant check to verify the data is correct. So they came back, and what you're seeing is the actual final data. So we were looking at all the details, and then what we did is we superimposed the shaft. We located where the bearings were, because all of this was critical. I had to know where the thrust faces were, which we'll talk about. So when we did this, we had the information on the original motor. We had the information now on the motor on site. We were able to superimpose the stator as the top view over the pit, and then, obviously realize that if I were to put the stator in there, it would drop right down into the pit. But that was a good thing, because it identified that now we could build some kind of an adaptive device or base to mount this motor on to span that pit. And then that was the original motor outline. The original motor spanned to the steel plates. But you could see the new proposed motor was longer and narrower. The original motor was wider and shorter in the axial distance. So here were the summaries and challenges from all this information. The EP motor, I'm just going to call it the EP, that's the spare. We had to span, we had 16 inches on each side to work with, but we had to actually span 27 inches to get to the solid support. And then the motor was about 51 inches longer. The adapter base, as we were starting to figure we had to build some kind of an adapter base, the motor, if you're familiar with motor terminology, the D dimension is the center line of the shaft to the bottom of the motor foot or to the base, a critical piece of information. On the original motor, it was 24 inches, center line to the base. Our motor was 37. So clearly we were going to be sinking in the floor further with this base. So just things we needed to know. Our motor was longer, like I said, so we identified that we probably were going to have to add gussets to those I-beams. The EP motor would have, we needed to duplicate the shaft of the original motor and somehow get that installed into the new motor. And to that point, because the shaft was so large, that was one of our challenges at the time, that we didn't know if we were going to be able to do it yet, because it required additional engineering. Couplings, the customer had no spare couplings, believe it or not, because they had no spare motor. So they had no drawings, they had no detail. So we had to reverse engineer everything here. Slip rings, no spare slip rings, same thing. Had to reverse engineer and figure all that out. Then do a load study or a power study to see what was really going on when we monitored the voltage and current and so on. So I understood their highest load condition. And then lastly, an engineering design assessment. So at this point, we passed like step 1, but we had so many more steps, and I wasn't even sure the motor was going to work. So we started chugging down through the list. So a lot of missing pieces at this point. Some of you that worked on the project know that it spanned a long period of time. And then we happened upon a series reactor. So when I was talking to the customer and I said, how was it connected? And they said, just connected directly across the line. Well, they did not even know that they had a series reactor in series that was reducing the voltage to give it a soft start. We stumbled on this. There was a cabinet in the basement, and I said, what's in that? And the guy goes, I don't know. We opened it up, and there was a series reactor. I mean, it sounds ridiculous, but this plant was very old, and the people that were involved, that would have known had retired, and the motor had been running, and the reactor never had issues, so nobody ever really had to question it. Kind of silly. But this was another piece of the puzzle that I had to incorporate in the design of our motor to know that we had this. And to be honest, the series reactor was a good thing because it allowed a reduction in voltage, a soft start. So a series reactor crammed in this cabinet, but when it was closed, you couldn't tell. So the next step was power monitoring. So we went on site with, actually the customer had some equipment, and they monitored the 3-phase voltages and currents and the excitation. They couldn't monitor power factor. I wanted them to, but they couldn't. But I lived with that because that's really what I needed to know. What does this thing do under its highest load swings? How does it react? And for me, really, all I was concerned about was how wild does the amperage change? How is that going to impact the motor that I'm proposing? So we studied all that, and we identified that the amps were varying from 175 to 195, and what they told me was their heaviest load material that they were dealing with. So no problem for the original motor. Original motor was good for up to 234 amps, but could have been a problem for our proposed motor because it being a unity power factor, not as big capacity synchronous motor, it was 176 amps. So right away, a red flag, it could overload at like 20 amps. So I use that information to summarize with the customer and say, look, you've got a 30-year-old used machine here. It potentially could work, but you have no reliability using this machine. And in particular, it had a cutout coil. So it wasn't just a stator winding, but it also had a bandage on it where a coil was cut out. So it wasn't going to be a balanced winding. And so we convinced them that this is a good move. You need to rewind this stator. So that's ultimately what that study did for us. It identified the need to rewind and maybe upgrade the stator and redesign. So the engineering assessment, we evaluated, driving those 6 DC generators. And then we had to evaluate whether we could redesign it to the higher horsepower. So the electrical design, when we did this evaluation, it's going to review the electrical design of both stator and rotor, thermal considerations, which are really important, starting conditions with that reactor, and then keep in mind after it gets synced, the reactor is then pulled back out and you have full voltage. So the reactor is only there on start. So we had to look at all those conditions. And then other factors, we were using the original stator and we had to work within those space requirements. The slot was only so big for a coil. Same with the rotor. The rotor had fixed pull pieces. We didn't want to go down that road. We could have. We didn't want to go down that road because it was just going to keep adding costs to the project. We were trying to save the money. So performing the design changes were a balance of several variables while performing numerous calculations, changing one thing at a time, and literally one thing at a time, looking at the output. Okay, that doesn't work, so changing it again or adding something to it and reiterating and repeating this over and over until we came up with what we thought was a design. And then we had to look at it from a practical point of view. Could we actually make it? Did it make sense? And we ended up coming up with a design. I'm not going to belabor this because I could talk for an hour or more just on the design. But what we did is we took all the details, all that data that I talked about from the original motor, all that was crunched. That information was calculated, and we looked at the losses. We looked at the torque of that motor. We looked at the field winding. We also looked at it with the two different reactor settings that we chose, 1.96 and 3.62 ohm reactor values, because we needed to know, okay, which one might be the best choice for this motor. And went through the losses again, did V-curves, which essentially helped us identify where this motor is going to operate amperage-wise on the stator, but also amperage-wise on the rotor. But it helps you understand the limitations of the existing machine. So we went through all of that, and we were able to redesign it from a 5250 to a 5500. We were able to redesign the rotor to have a stronger magnetic field and be able to create reactive power, because the original was a unity. We tweaked out 0.9. Actually, the design could work to 0.9, but we couldn't get to 0.8. It would generate too much heat. We'd have to try to redesign everything. Both windings insulations obviously were increased with today's insulation, the stator with Class F, the rotor with Class H. Class F is 155 C maximum temperature. Class H is 180 degrees C. The reactance values, we looked at both of those values. And lo and behold, we found out, because even at this point, the customer didn't know what connection they were on the reactor, because nothing, all you saw were leads going into the reactor, and the taps were inside the box. And you couldn't tell even when you looked in the box what tap they were on. So we had to figure that out. And lo and behold, their reactor setting was actually at 1.96. So that was a nice thing, because we realized, okay, that wasn't going to be something we had to mess around with when this thing was pulled out. And the performance of this machine ended up being really good for the 6-driven generators. A point to be made here, because I couldn't keep this in, the inertia, we did not have, in the beginning I said it's important to have the load speed versus torque curve and the load inertia. That info wasn't known. The only thing known was it was driving these 6 3 DC generators here and here. The fortunate thing is they had spare armatures. So when we found that out, we went to their warehouse. We got physical information on the armatures, the weight, and we took that in to be able to calculate inertia. So that's how we came up with inertia.